Hello everyone, my name is Gyeongsik, and I'm a postdoctoral associate at Korea University. This paper is a joint project I've worked on with my colleagues Yeonho Yoo, Minkoo Kang, Heesang Jin, and Professor Chuck Yoo. Cloud data centers deploy services from multiple users known as tenants. Between the virtual machines or containers of tenants, the network connections of tenants should be separated or isolated. To achieve this goal, cloud data centers use network virtualization. One type of network virtualization is SDN-based network virtualization, which provides programmability to tenants. In here, programmability means that the tenants can freely compose its network topology and manage all switches in a given network. The programmability toward virtual network has been motivated by various in-network optimization studies being actively researched recently. For example, for the physical network as shown in the figure below, network hypervisor, a central controller for virtualizing the physical network exists. Then, each tenant executes its SDN controller to manage the virtual network provided by network hypervisor. Also, tenants can create its own VN topology by requesting one from the network hypervisor. The topology is created by the mapping to the physical network resources as in the figure. The created virtual network topology resources are connected to the tenant's SDN controller so that the SDN controller can freely manage and program them. When the tenant wants to make a packet flow between entity I and J in the figure, the SDN controller performs routing. When the calculated path is VS1 to VS4 as figured, the flow rules for the first switches are sent. Receiving the flow rules, the network hypervisor finds the corresponding mapped physical switches and installs the flow rules on the physical switches. This scheme is widely focused as it provides flexible and programmable virtual networks to tenants in the clouds. However, one significant problem is that it can cause a problem on bandwidth isolation guarantee. Nowadays, various services like OTT, cloud storages, and machine learning frameworks are actively serviced through cloud. In this situation, each service has specific requirements on bandwidth. For example, some applications could request the minimum bandwidth that should be always provided for the service, or another one can request the maximum bandwidth that can be provided to avoid too many fees. Also, minimum and maximum bandwidth requirements could be required at the same time. Keeping such bandwidth requirements while maintaining isolation between tenants is called bandwidth isolation guarantee, and it's an essential technique that data centers should provide. However, in the context of SDN and B, the bandwidth isolation guarantee remains a research challenge. As you can see in the table below, many network hypervisors have proposed improving various aspects of network systems, such as multi-tenancy, scalability, or network support for VM migration. However, to the best of our knowledge, bandwidth isolation guarantees have not been discussed or solved in the previous studies. So we think that this makes the realization of SDN-NV technology truly challenging. In fact, bandwidth isolation guarantees have been studied a lot in other NV technologies because it is the essential one in cloud. The studies mostly abstract the situation through a host model. In a host model, the tenants' entities such as virtual machines or containers are regarded as being connected at a non-blocking switch. The tenant then requests the bandwidth requirement between the entities from the non-blocking switch. In the example below, 3 tenants request 500 megabps each, and the capacity of the physical link and switch are all 1 gigabps. With this model is feasible in existing data centers because the network resources between entities are totally controlled by data center operators. So the non-blocking switch can be mapped to any physical network resources. So, based on these abstractions, data center operators solely perform network routing that satisfies the requested bandwidth for the 3 tenants. When all tenant entities are attached at switch A and B, and the link capacity is 1 gigabps, the demand of all tenants can be satisfied by providing packet forwarding paths separately for each tenant like this. However, in SDN this scheme has a critical limitation. In SDN a tenant can perform routing over its virtual network, so the forwarding path is given in addition to the bandwidth requirements. For example, in this situation, let us assume that SDN controllers of 3 tenants generate packet forwarding paths as A, B, C, D. Then, this link becomes overloaded. Even the physical network has spare capacity in its network, and considering that data center constitutes its network topology as multipath one, there is a space for optimization for SDN. As a solution to this problem, this paper suggests T-Visor. T-Visor achieves both goals. First, in addition to the bandwidth requirements abstracted by a host model, it should preserve the calculated forwarding path from the tenants as well because it maintains the VM programmability. Second, T-Visor also achieves the bandwidth isolation guarantee by utilizing multipath routing. The desired result of T-Visor is that it reserves a certain bandwidth requirement on the path calculated by the tenants and generates an additional path for bandwidth isolation guarantee. In the example below, we can satisfy all 3 tenants' requirements by reserving 500 MDPS on tenant 1 through A, B, C, D path, and dividing the requested bandwidth by generating new path for tenant 2 into half on the path created by the tenant, and half on the new path through multipath routing. Also, for tenant 3, half and half of the requests are resolved similarly. To accomplish such goals, T-Visor comprises 3 main components: path virtualization, bandwidth reservation, and path establishment, which will be explained one by one. The high-level workflow of T-Visor is as follows. T-Visor first receives the bandwidth requirements from tenants. The requirement in T-Visor is defined per entity pair, which is the source and destination host. Also, T-Visor periodically updates the total and remaining link capacity of the physical network for bandwidth reservation for further steps. When the entity pair generates new traffic, the first switch receiving the packet notifies T-Visor of the event. T-Visor delivers the event to the corresponding SDN controller, and the SDN controller calculates the forwarding path for the received event. The results are delivered to T-Visor in the form of individual flow rules to be installed as virtual switches. Based on the received flow rules, T-Visor operates for the bandwidth isolation guarantee, and after all processing, the flow rules installed for the physical switches are generated. When flow rules are received, they are dealt with path virtualization. Specifically, vPath abstraction collects the flow rule per entity pair by checking which host pair the flow rule processes. For the collected flow rules, T-Visor crafts virtual path by rule training that identifies end-to-end paths created by SDN controller. From the first rule training checks the final output port of the flow rule and connects the output port to the input of the next flow rule. For example, in the figure, the packet for the first switch is coming from port A in switch 1 and goes out to port B of the switch 1. Then rule training finds the connected port to the output port in the physical network. In this example, port B of the switch 1 is connected to the port C of the switch 2. Then it can find the next flow rules in this manner. By following this, T-Visor serially discovers the end-to-end path created by the tenant. After virtual path is crafted, physical paths are generated through multipath derivation. In multipath derivation, 2 kinds of physical paths are created. The first one is the main path that is generated via topology mapping to the virtual path. Because the main path is the one created by the SDN controller, T-Visor always installs the main path in the physical network. As in the figure below, the main path is determined by the physical switches mapped to the virtual path. Another type of physical path is extra path. When the main path alone cannot support the bandwidth requirement between entity pairs, an extra path is created. The virtual path and multiple physical paths are mapped and maintained through the path chart. Through this mapping, when the SDN controller modifies or removes the virtual path after its installation, T-Visor applies similar actions to all relevant physical paths. In addition, multipath derivation operates together with bandwidth reservation. Bandwidth reservation calculates the amount of bandwidth to be reserved on each physical path and triggers extra path creation as needed. The first type of bandwidth reservation is for minimum assurance. The minimum requirement is the value that each entity pair is always provided as its bandwidth value. Let us assume that in the physical network below, all links and switches support 1 Gbps. Two entity pairs request 800 Mbps as their minimum, and the main paths are A, B, C, D, and A, G, D respectively. In this case, they can be satisfied by reserving 800 Mbps for the two main paths without creating extra paths. In the same network, let's assume another entity pair with same minimum requirement, 800 Mbps, and main path of A, B, C, D. Then its minimum value of 800 Mbps cannot be reserved on pair 3's main path. And this is because the spare capacity on the physical links for the main path is only 200 Mbps. To make fair reservations for all entity pairs and avoid additional regulations on already reserved bandwidth as much as possible, which could incur additional overheads, T-Visor performs the following. T-Visor reserves a portion of the minimum on each main path, which is defined by the bandwidth reservation ratio. For example, when the ratio is 3/5, pair 1 and pair 2's main path is reserved at 300 Mbps. The remaining minimum of pair 1, 500 Mbps, is reserved on a newly created extra path like this. So the requirement of pair 1 is satisfied. In the similar manner, pair 2 can also be satisfied. Then, pair 3's main path can reserve its 300 Mbps on the main path, and the extra path can be installed with 500 Mbps. So all three tenants and their pairs can satisfy its requirements. In addition to this example of high-level operations, our scheme contains careful considerations for utilizing network capacity and access controls, which are included in our paper. In addition to minimum assurance, T-Visor provides additional bandwidth to the physical path. The additional bandwidth is given within the maximum requirements given by each tenant. The max assurance runs separately from minimum assurance and increases the bandwidth for the existing physical path. For the ideal network capacity of its physical path within its maximum bounds, T-Visor provides three policies, such as dividing the capacity equally, proportionally according to the minimum value, or the actual network usage based on network monitoring. After calculating the physical path and bandwidth reservation, decisions are implemented in the physical network through the path establishment. Based on the designs, we implement full systems of T-Visor and conduct evaluations as follows. We compare T-Visor to Libera and Libera plus RL. Libera is the latest open source SDN solution, which does not have any kind of bandwidth isolation guarantee schemes. Libera plus RL is the case for comparison of existing host model-based studies, which is applied to SDN. Evaluations are conducted on 4 refractory topologies with up to 4 tenants. In the paper, we comprehensively provided the evaluation cases, changing the number of tenants, amount of minimum and maximum requirements. We only introduce representative results in this talk due to the time limit. First, we discuss the bandwidth isolation guarantees through the throughput values that each entity pair gains. The X mark in the figure shows the minimum requirement of each entity pair, and the circuit mark is the max requirement. First, with T-Visor, all entity pairs gain throughput near the max requirement. This leads to a near zero error rate for the bandwidth isolation guarantee. Second, in the case of Libera plus RL, where existing studies are applied on SDN and B, some entity pairs gained 42% less throughput on average than the minimum requirement, which doesn't meet the bandwidth isolation guarantee. Moreover, simple bandwidth limiting cannot provide additional bandwidth, so all entity pairs do not show higher throughput than the minimum requirement, even with the spare network capacity. In the case of Libera, which doesn't have a bandwidth-related scheme, entity pairs compete against network capacity. As a result, some entity pairs show very high throughput, but some entity pairs show 47% less throughput than the minimum requirement. Also, there is no means to limit bandwidth, so the bandwidth isolation or guarantee cannot be delivered through this scheme. In short, while T-Visor shows near zero error rates, Libera plus RL fails to satisfy the minimum, which leads to poor utilization. Libera also does not have any restrictions on the max requirement. We summarize the error rates on more various situations. When the number of tenants increased, the figure shows the error rate at the minimum value. Here, error rate means the extent to which the bandwidth given to entity pair violates the minimum. So the minimum error rate is the amount of bandwidth less than required. For the highest error rate in the graph, T-Visor shows a 0% error rate, while the other two show higher values. In terms of the max, T-Visor shows a 2% error rate. Note that Libera plus RL has no choice to show a 0% error rate for the max, because Libera plus RL does not provide any additional bandwidth higher than the minimum value. So it shows less network utilization than T-Visor or Libera. Finally, we provide the system overheads of T-Visor. Because T-Visor installs more multiple paths than existing solutions and uses additional messages for bandwidth reservation, the control traffic increases by up to 2.9 times. However, the amount of entire traffic during the experiment ranges from hundreds of megabytes, which we think is tolerable. Also, in terms of memory consumption, we carefully designed and implemented the internal structure, so the consumption is quite similar to existing solutions. Up to now, we have presented T-Visor, the first bandwidth isolation guarantee framework for SDN and B. Through full system implementation and comprehensive evaluations, we have shown T-Visor generates near zero error rates on both minimum and maximum bandwidth requirements with reasonable overheads. So that concludes my presentation on our paper. Thank you again for your time, and I'll be glad to answer any questions you might have, or you can also email me if you like. Thank you.